Alright, this is virtual lecture number 1, dealing with boron clusters, boranes and carboranes. And so for this, you want to refer to this handout, which was given out in class and is also available online. It summarizes a lot of what we're going to talk about here. And so, the topic that we'll start out with is higher boranes. And so what these are the boron analogs, if you will, of hydrocarbons. And so like carbon and hydrogen, you can form a very diverse array of compounds with long chains, short chains, branch structures, ring structures. Boron doesn't do exactly quite that, but what it does do is form a whole bunch of different clusters that have certain geometries, 3 of which we'll focus on here in this course. And so boron clusters have highly delocalized molecular orbitals. We talked about this in the context of B2H6, but it's even more pronounced in these things. And so these do have BHB bonds that are 3 center 2 electron. They also have boron-boron-boron bonds, which can be 3 center 2 electron, or even less. And so when we get into the pictures of these things, you'll see what we mean by that. And so as you might imagine, these things can have quite complex structures. And if you consider what they look like, you'll see this term here. They're referred to as deltahedra. Now, don't worry about the term yet, but this applies specifically to closo structures, although you can find it in some of the other structures. Why is this called this? Well, a lot of these things will have the following repeating unit. Three boron atoms arranged in the form of an equilateral triangle. And so they arrange themselves in this way. And so if you take the borons out and draw an equilateral triangle, what you see is that, and that looks like the Greek uppercase letter delta. And so that's the origin of the term for these things. Now what these do is they sort of fuse together with one another by sharing these edges. And when they do that, they can make very complex structures having 8, 10, 12, 20, up to essentially infinity boron atoms in the structure itself, along with some hydrogens or some carbons or even other things like group 15 elements. So before we jump into the structural analysis, let's take a look at the synthesis. These processes are actually sort of what you don't want to do as a synthetic chemist, where you want to make a target molecule, for example, and know exactly how you got there. These are actually quite complex, involving a number of steps. And the mechanisms are most certainly, in most cases, not understood. And so it takes a lot of practice to learn how to make these things. And in this case, you do actually do this in laboratory. To change around the structure, you have to go through one of these synthetic pathways to do this. And so, again, this is mostly FYI. This probably won't turn up on, at least not on an exam, maybe on a homework, fill in the blanks of what you're doing to construct one of these clusters. The starting material is the boron hydride that we talked about in class for a couple of lectures, B2H6. And this is typically done at a fairly mild temperature of 125 degrees C. And so the first thing that you do with this when you heat it up is you break it apart into its monomeric units. And so whenever you see these square brackets around something, what that means is that that particular species, whatever its formula is unstable. Meaning it is generated in the reaction, then it immediately reacts with something else. You can't, for example, isolate this and put it in a bottle or something like that. Okay. So we talked about that in class too. This does not exist this way. It exists as the dimer. And that's most certainly the case here. However, when you heat it to 125 degrees C, you do drive the equilibrium to the right. And then this starts to get consumed right away, and so therefore, according to Le Chatelier's principle, you're going to deplete this and force the equilibrium even further to the right. So the first step is generating BH3, like this. Next, that actually combines with the dimer to give the first, if you will, cluster formation. So B2H6 combines with the unstable BH3 that's generated. And in an equilibrium, which is fast, which means the product that I'm going to write down here is interchanging very quickly with the reagents that they start from. That generates B3H9, which is also, as per the square brackets there, unstable. Now, what that actually does is once it's generated, it does equilibrate with these two species, but it also undergoes another process which is slower. So this is the slow step, and it also proceeds pretty much to completion, which is why it was drawn as an arrow instead of an equilibrium. This generates a cluster B3H7, and it also involves the liberation of hydrogen gas, which actually bubbles out of the reaction. And so you get an equilibrium process in competition with the hydrogen elimination process that then allows for the beginning, if you will, of the buildup of this material. So then, if we take the unstable generated B3H7, and that combines with more BH3, which is still present in the reaction, that gives you, in equilibrium, B4H10. And this is the first example, the lowest example, the least aggregated example, if you will, of a stable boron-hydrogen cluster. So generally what holds true is that you need 4 or more boron atoms to have a stable structure. And there's something special about the ratio there of boron to hydrogen as we get into this. And when we do discuss the different structural motifs, you might look at this and immediately recognize that it's an arachno cluster. We're coming to that. Then what happens is sequential reactions with borane. So this stuff sort of persists and stays around, and in equilibrium that lies more closely to the product side. What we get out now is B5H11, which is also stable. And that's another hydrogen elimination process. So the aggregation steps, if you will, from a stable thingy to another stable thingy involve the reaction of a stable cluster with BH3 in its monomeric and active form to give you a larger molecule, and this is almost always accompanied with hydrogen extrusion, H2. So, without going through all the tedious details, buildup can continue. And so, this process provides a whole bunch of clusters. And so you isolate these things in the process of the buildup by extracting them out or fractionally distilling them out or what have you. And so from just that combination of BH3 and B2H6, what we get are a whole bunch of things that are stable. We already saw B4H10 and B5H11. Then by another combination of this with BH3 followed by hydrogen extrusion, we can also get B6H10, B6H12, B10H14, and on and so forth. And so, again, we won't spend a whole lot of time going over these processes because, like I said, they are complicated and difficult to understand. But the one last synthetic thing I'd like to mention is the following, and that is the synthesis of the borohydrides. Now, the "ide" at the end tells you this is probably going to be an anion. As a matter of fact, that's what it is. And so, the most stable things that you find for these will have a very specific formula. So let's look at how this is done, starting with B2H6. We need 5 of those. If you combine that with 2 equivalents of sodium borohydride, which is a compound that we talked about in lecture on Monday, and you apply or put this in some trimethylamine at 180 degrees C, what will happen is you will get lot of hydrogen evolution and the formation of the prototypical and most commonly referred to boron hydrogen cluster, and that's this one right here. And so now these brackets do not symbolize that the thing is unstable. If we take away the two sodium cations here, what we have is the following anion: B12, H12, 2-. This is the most common example of one of these things that you'll probably see. It does have, again, the closal structure, which we'll get into that in just a few minutes as to what that means. And it's very stable. And so the parent ion, if you will, always have the following formula. B sub n, H sub n, 2-. So these are salts with some cation. They can be alkaline metals, they could be alkaline earth, they could be ammonium, phosphonium, etc. So there's some cation with a +2 net overall charge associated with this thing. But these are the common and stable boron hydrogen, or borohydride if you prefer, clusters. And so what this formula tells us is the following. If I've got 6 borons, I've got 6 hydrogens. If I've got 8 borons, I've got 8 hydrogens, and so on and so forth. And as you can see from the synthesis that was up here, these are actually quite a bit easier to make, and their process is at least rational in terms of you can stuff the thing up and make the compound itself. And so these things actually end up being the starting materials for a lot of other things. So just one more synthesis for the heck of it. Again, starting with our favorite dimer here. If you combine that with lithium aluminum hydride, which we'll talk about when we get to aluminum, this is isostructural and isoelectronic with borohydride, which we already mentioned, but its chemistry is a little bit different. That will give you, at 160 degrees C, Li2, B10H10. So note, we have a salt of the B10H10 2- anion. Okay. So now, the actual, sorry, my computer keeps fading out, that's why I'm touching the mouse pad up there. Important part of this that we're getting to. Boron cluster geometry. So one of the things I want you all to be able to do is to figure out the geometry of a cluster given just its formula. And it may sound like a somewhat daunting task, but trust me, it's actually just formulaic. And once you get the hang of it, it's quite simple. So this depends essentially on one thing and one thing only, which is kind of weird considering how complex these structures are. There's a simple term that defines what structure you're going to get. And this depends on the total number of electrons, not just the total number of electrons, though. The total number of electrons available for skeletal bonding. Not just the total number of electrons, but the number of electrons that are available to hold the dihedral framework together. So how many electrons are available to do this? That's the question. Once you answer that question, then you know what the geometry of it is. And once again, these things are going to be highly electron deficient, which means if you consider a regular covalent bond, a two-center, two-electron bond, where you've got two electrons between two atoms holding those two atoms together, what you'll find is that if you look at the structures of these things, and again, pretend rather that each dash in them represents a two-center, two-electron covalent bond, then see how many electrons there are actually totally holding the thing together, you find that there's not the number that you would expect. And so we can start this discussion with the borohydrate anions. Once again, this will always, or these will always have the formula as shown here. Bn HN 2 minus. All right? If you see that, you automatically know that this structure is closo, and that's normally written in italics, but again, that's a semantic thing we won't worry about. What does this thing look like? Well, let me refer you to page 3 of your handout, and more specifically, page 4 of your handout. Now this one, page 4, is using shorthand dash wedge notation, like when you write a hydrocarbon like that, right? What does that mean? Well, there's a CH3 here, there's a CH2 there, etc. Then you ascertain the formula from that. So this is doing the exact same thing as that is, but it's a little harder to get used to it. Okay? So let's instead start with something a little bit more simple. And we're going to go with the top of this flow chart shown here on page 3 of your handout. Okay? So, what's the anion in question? Closo, B6H6 2 minus. So if you look at that and you count the number of sides, how many are there? There's 4 on the top, 4 on the bottom. And let me specifically change that, because it is important to use the right word here. How many triangular faces are there? 8. This is an octahedron. Okay? So again, I'm making a joke about it, but if you do pull out a D8 from your Dungeons & Dragons or whatever role-playing dice game, that's the shape of it. You've seen this before, probably in Vesper theory, but what you have is an atom at the center of the octahedron, and then ligands making up the face, for example. SF6 is octahedral. There's a sulfur at the center, and here's the triangular faces. I'll just draw one of them. It's right there. Those are equilateral triangles. So the difference between that and our stuff here is that you don't have anything at the center of the octahedron, and you have borons at each corner. So this is the anion that we're talking about, and it's closo. What does that mean? This term means we have a deltahedron. It could be a tetrahedron, an octahedron, an icosahedron, what have you. A deltahedron, which means you've got equilateral triangular faces held together by shearing edges. You have a deltahedron with a BH group at each vertex. So, if you look at this up close, the boron is the large shaded sphere, the hydrogen is the small white sphere. At each vertex of the octahedron, each corner of it, of which there are 6, you have a BH group. Closo means exactly that. It's a deltahedral structure where each vertex is, if you will, occupied by a BH group. Now, let's do some electron counting. So in our simple example here, and believe me, this is a simple one, how many valence electrons do we have total? So this is something, again, that's probably old hat, but that we need to actually reapply in a different way, okay? So how many total valence electrons are there? We've got 6 borons. Each boron's got 3 valence electrons, right? It's in group 13, so it does. We have 6 hydrogens. So there's only 1 valence electron for hydrogen. Don't forget the -2 charge, though, because there's an excess of 2 electrons in this structure, which is actually important because it's a key feature rather, to holding it together. Okay. So what if you add all that up? Well, what do we get here? 18 plus 6 plus 2. There's our magic number, 26. This cluster has 26 valence electrons holding it together. All right, so now before we get into anything more, once again, take a look at the picture here. What we want to know is how many of those electrons are used to hold that together. How many of these things hold the B6 cage, if you will? Together. So our magic number, our total number is 26. Based on what you're about to see, this will allow you to determine that this is a closo structure. Of course, you actually already know that, because if you remember that BnHn2- is closo, you don't have to apply any formulas or anything like that to figure this out. So how many electrons hold that B6 cage together? That's the next question we got to answer. And we can do that if we understand any boron-hydrogen bond at a vertex is a normal two-center, two-electron bond. So just like a carbon-hydrogen bond, exact same thing. So this is akin to the terminal hydrogens, 1, 2, 3, 4, and B2A6. Okay? So what that means is that each one of those vertices, has a boron-hydrogen bond, which has 2 electrons, which means each one of them takes 2 electrons from the total. Okay? So if we can figure out how many bonds, or how many electrons there are used to form the 6 boron-hydrogen bonds, then we know how many are left over to hold that cage together. So this is quite true. For hydrogen bonding the hydrogens to our cage, we have 12 electrons involved. Okay? 6 boron-hydrogen bonds. Don't believe me? Look at the structure. There's 6 of them. Each one of these dashes here between the boron and the hydrogen represents 2 electrons. And so that means the number of skeletal bonding electrons equals total electrons minus the total number of electrons used to form the boron-hydrogen bonds, in this case 6 of them, at the vertices. So, to make a long story short, oops, I don't want to erase that yet. The number of skeletal electrons is 26 minus 12, or 14. So what that means is that for that B6 cage, only 14 electrons are there holding that whole thing together. The skeletal bonding means the bonding in the boron component only, and it only takes 14 electrons to hold the thing together. So is that strange? Is that electron deficient? Let's look. If we again take our picture, let's count the number of edges. And you can go ahead and do that on your own. However, let me throw this at you. And it's actually worth memorizing this because it'll save you from counting or trying to, did I count that one, miss that one, whatever. When you get up to 30 boron atoms, for example, good luck trying to do that. So these formulas are something you'll need to know for an exam. You can look them up in your notes in the homework, of course. We have n vertices. To simplify that down, it's the number of boron atoms. Any deltahedron that's closo will have 2n-4 faces, n being the number of boron atoms. And 3n-6 edges. So those two formula there, 2n-4 and 3n-6, be very important for doing the homework assignment that you have, and also this is going to show up on the second exam. So learn them, because those are one of the things you'll have to know. Okay. So what then do we do with this? Well, let's look at our cluster that we have at hand. There we go. N equals 6. There's 6 boron atoms. There's 6 vertices. So we already said this is an octahedron. Let's see if we're right, or does our formula agree with what we already know. Applying this formula here, that tells me that I get 12 minus 4, or 8 faces. So yeah, it does work. And in fact, it'll work every time, as long as you remember. Closo only. You cannot apply this to nido or arachno structures, and we'll see what those are in due course. But it works. Hey, that's good. Let's also hit it up for the number of edges. What we're going to do is apply that. So we get 18 minus 6, or 12. So again, if you're familiar with this shape, you already know that that's spot on. That's exactly what we'd expect. So there we go. We've got, in our structure here, 8 faces, making it an octahedron, and there are 12 edges in there. So these formulae do work. Now what I want to do, just for the heck of it, is look at this. We have 12 edges, and we already found that there are 14 skeletal bonding electrons, meaning there's 14 electrons holding the B6 cluster together. Let's pretend for a moment that this were a hydrocarbon, or something that each one of these dashes here, meaning each one of those edges represented a 2-center, 2-electron bond. Then how many electrons would we need to hold that whole thing together? you would need 24 electrons. We don't have 24 electrons. We have 14. So 14 electrons hold together the B6 framework, that if this were carbon or something that strictly obeys the octet rule and doesn't do this electron deficient stuff, you would need 24 electrons, so 10 more than we actually have. And so that means most definitely that these are electron deficient, and that imparts some really interesting properties to them, as we'll see. Okay. So finally, for the end of this virtual lecture here, if you're a formula type person, you like to have a formula for everything. There is one for the number of skeletal electrons, and that is 2n plus 2. So there's two ways you can arrive at the number that we arrived at here. You can do it the way we just did. How many vertices are there? Okay, that each one takes 2 electrons, subtract from the total. Or this. Let's just make sure that this works. Again, n is the number of vertices. We got 6 of them. And lo and behold, 14 electrons. So it does. So you can remember that formula, or remember the technique that we used previously to do it. So in the next lecture, we'll look at some more examples of how to determine edges, faces, and things like this. And then we'll get into the Nido and Arachno structure.